and I want to invite our last speaker for this track back to the Academy, Dr. Amir Weiss from Faculty of Engineering at Bar-Ilan University, that will talk about AI-enhanced RF signal separation.
Great. So it's good to be here at AI Week, and especially in this great signal processing session. Before I start, though, I do feel obliged to mention one more time the hostages, our compatriots, and to express my strongest hope for their return home in peace and as soon as possible. Okay, so in this very brief talk, I'll be dealing with the signal separation problem in the RF domain, which so far has been comparatively less explored, at least from an AI perspective. And rather than sharing, putting the focus on new results that we've obtained, my goal today here is to introduce, or maybe to put in the front, this challenging forefront, and hopefully to engage your attention and interest so that as a community, we can accelerate the progress in some of these important upcoming problems. So let's get started. And usually, when people talk about or start to talk about the source separation problem, they mention the cocktail party, a term coined by Cherry in the late 1950s to describe our natural ability to extract or separate an acoustic source in a noisy environment, right? And of course, back at the time, there was no machine that was even close to do such a thing. Some 60 years later, as we all know, deep learning has taken us to a completely different place, right? When we have algorithmic and computational abilities that already provide solutions that are constantly getting closer to human abilities, right? However, today, and definitely in the near future, the auditory cocktail party is not the only party going on. And in fact, since the 1990s, we have witnessed a takeoff of the wireless technology and an ever-growing increase in the number of wireless devices around us. Of course, as Ziv already mentioned, right? I mean, we have smartphones, laptops, smartwatches, routers, you name it, right? I mean, the list just goes on. And as more devices are being added to this RF version of the cocktail party, we expect to see more and more signal collisions. Now, from the perspective of a receiver in a communication system, that means that on top of the desired signal, we'll probably see an interference signal. So it's obvious that we need to develop better and better interference mitigation or signal separation modules to cope with such scenarios. And in this talk today, I will focus on the single channel case, which is the case for receivers that are equipped with one antenna, okay? Now, let's consider a basic formulation of this problem. Assume that we have a device, such as this drone here, that we'll go back to, that wants to send a message to another device, right? And it's transmitting this signal that I will refer to as the signal of interest. Note that the receiver here has one antenna, as I mentioned. Now assume that another device is operating in the relevant reception range, such that our receiver observes a mixture of the signal of interest and another signal that could be a communication signal that is intended to another receiver, right? But from our perspective, it can be thought of as structured interference. And when I say structured interference, I mean rather than, for example, additive white Gaussian noise, right? So I want us, this is, for some reasons, this is a simplified signal model, but I want us to think about this basic formulation as the MNIST version of the RF signal separation problem. And the goal of this interference mitigation module, of course, is to take this time series that is the sum of these two components and to give us the best estimates in some sense of the signals of interest and as a result, of course, the interference. Now, a downstream task could be demodulation and decoding of the information bits. It could be anomaly detection or any other task that the system was intended to perform. Now, where could such a model be integrated? Of course, there are many possible architectures. This is the architecture that we'll consider. And what you see here is a typical block diagram of a simplified communication system where the upper branch is the transmitter, and this on the side, this is the channel. On the lower branch, this is the receiver. And our module, our interference mitigation module, is integrated right before the standard processing chain of the receiver that was originally designed to be fed with the interference-free received signal, right? So what are possible approaches for this module? Of course, there are many. Let's mention three. The first is very easy to implement: do nothing, right? And maybe before or in the early 90s, when there was very low probability to meet an interference or the power was very weak, this could work. But obviously, this is generally a naive approach that would not work today or in the near future. Another approach, which is very common, actually, in many systems, is to apply linear filtering. And this works well in some cases, and it could even be optimal in other cases. For example, if the signals S of t and B of t are completely not overlapping in the frequency domain, then, of course, standard bandpass filtering would provide even perfect separation, right? So for this reason, we would assume from now on that S of t and B of t are overlapping both in time and frequency. And this gives us an undegenerated version of this challenging problem that we expect to see. And a third approach, of course, would be to use tools from deep learning, and this is assuming that the relevant data sets of the underlying signal are available. And assuming that we have such data sets, then this approach could lead to performance that are at least as good as the best linear separator. And of course, it can go beyond when the optimal separator turns out to be a nonlinear operator. Now, as I said, neural networks are not necessarily needed, since there are cases where optimal or even perfect separation is attainable even by linear filtering, right? So an important question is why, and maybe as importantly, when should we use them? The short answer is when the signals involved are non-Gaussian and non-stationary. And in order to better understand this answer, let's consider a concrete and instructive example. So specifically, let's look at orthogonal frequency division multiplexing signals, or OFDM, which are very common in many protocols today. And without going into the details, if you're not familiar, let's just look at the time domain representation there. This OFDM signal can be thought of as a weighted sum, right, of orthogonal complex exponentials, which we call subcarriers. And the weights are the information-carrying symbols. These are denoted here by theta k. And theta k are just discrete random variables, right? So an OFDM signal is a linear combination of discrete random variables. Now, when the number of subcarriers is large, then this signal from a central limit theorem argument tends to look more and more like a spectrally flat complex normal random process. And that's very convenient to someone who wants to analyze the performance or maybe devise a model-based, if I use the language method. But of course, we know the structure and the generation process, and this is not a complex normal process. So that's the non-Gaussianity. And let's look at the temporal structure. What we see here is a temporal covariance matrix of a typical OFDM signal. And the interesting thing is that if we focus on short time scales, let's look at the small red square, then we see a scaled identity matrix, right? This corresponds to a white or uncorrelated signal, which is definitely stationary. But if we look at longer time scales, of course, we see that not only it's not white, it's not stationary, because it's easy to see that this matrix is not toplets. And this is due to something called the cyclic prefix, which I will not go into. But the important thing to get here is that there exists a strong statistical structure of non-Gaussianity and non-stationarity. And the important question is, can we exploit this structure and in turn translate it into enhanced performance in terms of interference mitigation? And what I want to show you now is that not only the answer is yes, but I want to show or maybe demonstrate how much we can improve, okay? So let's look at this video here on the left upper corner, and there's no sound, so while I play it, I'll explain. If you remember that drone, this video was taken by the drone, and of course, a video, any video, corresponds to a bit string, right? So we'll take that bit string, and we'll pass it through a processing chain of a transmitter, which means we'll add code, we'll map it to symbols, we'll put it on a pulse shaping function, and we'll create the signal of interest S of t. Now, we'll create a strong bursty OFDM interference, like the one we talked about, and add it after 3 seconds. And let's see the decoded message at the receiver that simply ignores the presence of the interference. Sorry, it always happens. It's about 3 seconds, so more or less here. And you see that, obviously, if the signals are overlapping in time and frequency, ignoring it leads to a severe distortion. Now let's look at the receiver that is equipped with the best linear separator, okay? It's an Oracle receiver because it has access to the joint statistics of the signals. So we first estimate the signal, and then we decode the message. Should start about here. Not really improving, but even if some, the distortion is still severe. Now let's replace this best linear separator with a deep neural network that was trained to separate these two types of signal and was trained to see an OFDM interference. So remember, 3 seconds, you start about here. If you look closely, of course, you still see a distortion. It's not perfect, but obviously the improvement is, let's say, at least significant, and most of the visual content and the visual information is preserved. So to get, thank you, thanks. So to get this quality of separation, as I said, we need to know how to exploit non-Gaussianity and non-stationarity, and for this, we want to process very long input vectors. And for this reason and other considerations, we converged in our development process to this modified unit architecture. And the unit was originally proposed for biomedical image segmentation, but has been adopted to other applications where the setup is typically a multivariate regression where the dimensions of the input and the output are the same. So in this sense, this was a good starting point for our purposes. I actually have much more to say about this, but no time, so I invite you to look in the paper or reach out, and I'll be happy to discuss. So this is one example, and this approach boils down to a one-dimensional regression formulation, right? But from a system perspective, it has a limitation that I want to mention. And the problem with this approach is that it needs a trained model for every mixture type, namely every combination of two pairs. All right? So in other words, it learns the joint statistics of the signal of interest and the received mixture, Y. And what happens if we have a long list of interferences? It means we need to save and we need to train a model for each pair. Of course, this doesn't scale. What could scale favorably is an approach that needs the priors only, the priors of the signals. And this would, of course, if we're able to develop such a solution, it would scale linearly with the size of that list I mentioned. So this leads us to a different approach. And in particular, if we choose the maximum posteriori criterion and we further assume statistical independence of the signals, which we didn't have to assume in the previous approach, then we end up with this objective that has two decoupled terms, each one correspond to a prior of each source, right? So we only need the priors. Moreover, if we want to optimize this objective using a gradient-based method, then we only need the scores, right? The gradient of the log probabilities, and as we know, these can be conveniently learned using diffusion models. So if we can learn these scores, we can devise an optimization algorithm, which we did, and you're welcome to look at the paper, our last NeurIPS paper. But here again, an important question is, how well can we learn priors of communication signals? As other speakers already mentioned, these are not images or audio. These are bits that were transformed, right? So again, I want to show you by visual demonstration. What we see here is a plot of a single carrier communication signal, right, that has a root raised cosine pulse shaping function and QPSK symbols. And of course, this is a complex valued signal, so we see the real and imaginary part. And what we see on the right is an example of a signal generated by our trained diffusion model. Okay, and of course, I think it's easy to see the statistical similarity, but we verify that these signals correspond after decoding to valid clean bit strings. So we have a model that knows actually, I think one of the speakers mentioned it, we have a model that knows how to generate synthetic signals. Of course, this method was also tested in accurate metrics versus the state-of-the-art benchmark and was shown to be superior. So these were two examples of AI-inspired novel solution approaches. But this was only one problem, and there are many problems ahead of us. Some of them are mentioned here in the slides. However, one exceptionally important mission we face as a community is the process of collection, organization, and dissemination of RF signals. These are not images, and unfortunately, they are not easily accessible. And of course, we know they play an instrumental role in developing new ML-based solutions. So to this end, me and my collaborators from MIT and MIT Lincoln Laboratory have created the RF Challenge, which aims to encourage the community, the RF community, the ML community, in developing new AI-inspired algorithms for problems involving RF signals. And the challenge includes other problems like the extension to the multi-channel case and the cyber RF anomaly detection. And I invite you to look in, go in the website, learn about it, and be a part of it. And yeah, we reached to the end of the presentation. So going back, my main goal here, as I said, was to let you know that the RF realm is filled with opportunities for ML-based solutions that will enjoy high gains and high technological impact. And I think if you want to make a difference, that's the place to be. So I hope you join me and others to this endeavor, and it was great sharing this here at AI Week. And with that, I'll hand it over back to you, Itai.
So thank you, Amir, and for solving my problem at the beginning for generating a communication signal.
You're welcome.
This concludes our track for AI for Signals for today. And I want to really thank Amir for his amazing talk. And let's hear about some questions from the crowd.
You mentioned that you were forced to train for each pair of desired and interference signals the network.
Mm-hmm.
Did you try to train on a bunch of interference? Let's say you have a list of 10 let's say a family of 10 signals of interference. Train the network once on this family, maybe enlarge the structure for it, and then hopefully it will mitigate in single train all of these signals.
Yeah, I think, okay, actually, great question. Maybe the key word is hopefully that you mentioned. And this is a very brief presentation of 17 minutes, but actually it compresses an effort of more than 3 years. So as other speakers already mentioned, actually using ML tools in this domain is very challenging. It's not that easy to get even something working, such as a regression problem. And so the answer is that we started with the very ambitious goals like the one you mentioned, and once we saw that nothing works, we came back to first principles to solve it. And just to refer to maybe the practicality of this approach, of course you assume that you know the two signals, but to detect the type of signals in a mixture is a much easier, generally speaking, much easier task. So of course, you generally need to train a classifier on these types, identify the signal types, and then apply the corresponding model. But this is generally an easier problem, and the separation is much harder.
Okay, thank you.
Yeah.
Hey, thanks for the presentation. In the final method you presented, you added the assumption that the two signals need to be statistically independent. What is the practical meaning of that? Like for example, if there are two radars in the two adjacent vehicles that are using the same frequencies and observing the same area, can I assume that they're independent?
So first of all, it's a good question. In the classical approach, it's common practice to assume that they are statistically independent. But where could it be important? For example, in the case of jamming, when you have a jammer that knows what you're transmitting and is actually modifying their transmitting according to what you transmit. So maybe there will be a relation that can be modeled as a statistical dependence. Not necessarily, but this is one example. But I think that in most scenarios, it's quite a fair assumption to assume that the signals, at least if you have two signals from two different communication systems, it's a fair assumption to assume that they're statistically independent.
Great. So let's thank Amir again.
Thank you.
Thank you so much for participating, and thank you again for all our 5 amazing speakers.